In the chapters linear programming problem formulation and linear programming graphical method, we have seen how to convert a word problem into an LP model and how to solve that using graphical method respectively. Now the graphical method of linear programming is useful when an LP problem involves two variables. However, if there is a third or a fourth variable, then the graphical method loses its utility. In those cases, Simplex method can be easily used to solve the linear programming problems. Simplex method can help in solving linear programming problems which involve any number of variables and constraints. This number can go to hundreds or even thousands. This technique is also used by computer programs to solve linear programming problems. So we'll see the various steps of solving these problems using Simplex method with the help of an example. So the example at hand is that a manufacturer specializing in the manufacture of gears intends to add two more types of gears to his existing product line. Both the types of gears will be worked in the blanking shop and in the gear shop. Now each gear of type A requires 20 minutes in the blanking shop and 40 minutes in the gear shop. Similarly, each gear of type B requires 10 minutes in the blanking shop and 10 minutes in the gear shop. Now the blanking shop and the gear shop have respectively 1200 minutes and 1600 minutes available per week. So this is the information regarding the time taken by both the types of gears in the blanking shop and the gear shop, and the total time available for processing in the blanking shop and the total time available for processing in the gear shop. Now the marginal profit for each gear of type A is ₹10, and for each gear of type B is ₹4. The manufacturer is in the market upswing and can sell as much as he can produce. How many units of each gear should be produced to maximize the profits? So basically, this manufacturer is in the business of manufacturing gears, and he wants to add two more types of gears to his product line. Let's say the first type of gear is type A and the second type of gear is type B. Now both these type of gears have to go through a blanking shop and a gear shop. So these are two different departments which have different type of machines, and each of these product types has to go through each of these shops to be converted into the final product. So A has to go through both of these and B also has to go through both of these. Now each gear of type A requires 20 minutes of processing in the blanking shop and 40 minutes of processing in the gear shop. So 20 minutes in the blanking shop and 40 minutes in the gear shop. Similarly, each gear of type B requires 10 minutes in the blanking shop and 10 minutes in the gear shop. So each gear of type B needs 10 minutes in the blanking shop and 10 minutes in the gear shop. The blanking shop and the gear shop have respectively 1200 minutes and 1600 minutes available per week. Now blanking shop can be used only for 1200 minutes per week, while gear shop can be used for a maximum of 1600 minutes per week. Also, we have been given that each gear of type A generates a profit of rupees 10, while each gear of type B generates a profit of rupees 4. So type A generates a profit of 10 rupees each, and type B generates a profit of 4 rupees each. Now, of course, we want to maximize our profits, and we do have some constraints in terms of the time availability of the blanking and the gear shop. So we want to find out how many units of each gear should be produced in order to maximize our profits. So let us see how we can use the Simplex method to solve this linear programming problem. So the first step in solving an LP problem using Simplex method is to construct an LP model of the problem. So in our example, we have two types of gears to be manufactured, gear type A and gear type B. And we want to find out the quantity of both of these types of gears to be manufactured in order to maximize the profits. So let us consider that X1 is the quantity of gear type A to be produced. And X2 is the quantity of gear type B to be produced. Now we have also been given that each gear of type A generates a profit of rupees 10 each. This is for A. Now, if the quantity of type A gears is X1 and each of type A gear generates a profit of rupees 10, then how much will be the total profit generated by X1 quantity? So we can use cross multiplication here. So one number of gear type A generates a profit of 10 rupees. So X1 number of gear type A will generate how much profit? Let's say this is Y. So here we can cross multiply. Y multiplied by 1 is equal to 10x1, or Y is equal to 10x1. So the total profit for X1 quantities of gear type A will be equal to 10x1. Similarly for B, the profit for each gear of type B is given to us as rupees 4. So same concept. for one number of gear type B, the profit is 4 rupees. So if the quantity is x2, then how much is the total profit? Again, cross multiplication. Y into 1 is equal to 4 times x2, or y is equal to 4 times x2. So the total profit generated by x2 numbers of gear type B is equal to 4 times x2. So the total profit generated by gear type A is 10x1, and the total profit generated by gear type B is 4x2. So the total profit generated for the manufacturer by producing x1 numbers of gear type A and x2 numbers of gear type B will be equal to 10 times x1 plus 4 times x2. So this is the total profit, and the objective of the company is to maximize profit. So our objective function for this LP model becomes maximize P, which is equal to 10 times x1 plus 4 times x2. And x1 and x2 are the quantities of gear type A and gear type B which is to be produced. So let's say this is our number 1. Now let us look at the constraints. So we have been given that each gear of type A needs 20 minutes of processing in the blanking shop and 40 minutes of processing in the gear shop. So for type A gear, let's say this is for blanking shop and gear shop. So each gear of type A needs 20 minutes of processing in the blanking shop and 40 minutes of processing in the gear shop, while each gear of type B needs 10 minutes of processing in the blanking shop and 10 minutes of processing in the gear shop. We have also been given that the total time available for processing in the blanking shop is 1200 minutes, while the total time available for processing in the gear shop is 1600 minutes. So basically our first constraint is the time availability at the blanking shop, and our second constraint is the time availability at the gear shop. So let's construct the constraints. So each gear of type A needs 20 minutes on the blanking shop, and we have x1 number of type A gears. So again the same concept as we had used here. One gear needs 20 minutes, so x1 will need how much? So cross multiplication, let's say this is y is equal to 20 times x1. So 20 times x1. Now each gear of type B needs 10 minutes on the blanking shop, and the total number of type B gears is x2. So the total time needed for processing all the gears of type B will be 10 times x2. So 20x1 plus 10 times x2. So this includes the total time that is needed for x1 numbers of type A gear and x2 numbers of type B gear on the blanking shop. However, we have been given that the total time available for the blanking shop is 1200 minutes. So this has to be less than or equal to 1200. So this is our first constraint. We'll call it number 2. Now let's construct the constraint for the gear shop. So again the same logic here. Total number of type A gears is x1 and each gear takes 40 minutes in the gear shop. So total time taken by all the type A gears is 40 times x1 plus the time taken by each gear of type B on the gear shop is 10 minutes. So the total time taken by all the number of gears of type B is 10x2. So 10 times x2, and the constraint of total time at the gear shop is 1600 minutes. So this should be less than or equal to 1600. This is our second constraint. We call it number 3. So number 1 is our objective function for the LP model. Maximize P, where P is equal to 10 times x1 plus 4 times x2. And 2 and 3 form the constraints. 20x1 plus 10x2 is less than equal to 1200, and 40x1 plus 10x2 is less than equal to 1600. And both the variables x1 and x2 have to be greater than or equal to 0. So x1, x2 should be greater than or equal to 0. So this is the LP model that we want to solve using the simplex method. However, in order to apply the simplex method to a linear programming problem, there are two conditions that need to be satisfied. Let us look at those two conditions. So the first condition is that the right hand side of each of the constraints should be non-negative. So in our case, the constraints are 20x1 plus 10x2 is less than equal to 1200, and 40x1 plus 10x2 is less than equal to 1600. And the right hand side, that is 1200 and 1600, both are positive. So this condition is met in our case. However, let's take an example of a constraint. So let's say you encounter a constraint like 8x1 minus 3x2 is greater than or equal to minus 6. So here the right hand side is negative. So if you have a constraint like this, then what we need to do is multiply both the sides, that is left hand side and the right hand side, by minus 1. So multiply by minus 1. So then our equation becomes minus 8x1 plus 3x2 is less than equal to 6. Now note that the sign of inequality has changed in this process. Let us understand why this happened. Now we know that 2 is less than 6, right? The number 2 is less than the number 6. Let's multiply both the sides by minus 1. So minus 2 and minus 6. But now minus 6 is smaller than minus 2. So the inequality sign reverses. So that is the same logic which we applied here. Now let's look at the second condition. So the second condition is that each of the decision variables of the problem should be non-negative. Now in our case, the decision variables are x1 and x2, and both of them are considered to be non-negative. However, sometimes a problem might have a variable which is unrestricted in sign. So it can assume negative values as well as non-negative values. For example, let's say that the LP model is maximize z, where z is equal to 5x1 plus 7x2 minus 2x3, and this is subject to the constraints 2x1 plus 5x2 plus 3x3 is less than equal to 80, 5x1 plus 2x2 minus 2x3 is less than equal to 30, x2 plus 6x3 is less than equal to 42, and x1, x2 is greater than or equal to 0. So here there are three decision variables, x1, x2 and x3. And it has been given that x1 and x2 should be greater than or equal to 0. However, x3 is not bound by that constraint. Hence, it can take a non-negative value. However, this is not acceptable if we want to use the simplex method. So this situation is handled by introducing two new variables. Let's say in our case x4 and x5. Both of these are non-negative and are such that the difference between the two is equal to x3. So x4 minus x5 is equal to x3. So basically the problem was that we had x3 as one of the decision variables which could take any value, a 0 or a negative value. However, we will replace this variable by two new variables which are non-negative, and the difference between the two will be equal to the other variable, that is x3. So let's see how this will change our LP model. So our objective function was maximize z, where z is equal to 5x1 plus 7x2 minus 2x3. So maximize z equals to 5x1 plus 7x2, and now instead of x3 we'll introduce x4 minus x5. So minus 2 times x4 minus 2x4, and this minus minus will become plus, so plus 2 times x5, plus 2 times x5. Now the constraints 2x1 plus 5x2, so 2x1 plus 5x2 plus 3 times x3. So this becomes plus 3 times into bracket x4 minus x5. So this becomes plus 3x4 and then minus 3x5 is less than or equal to 80. The second constraint, 5x1 plus 2x2 minus 2 times x3. So this becomes minus 2 times x4 minus x5. So minus 2 times x4 and then minus will become plus. So plus 2 times x5. And this is less than or equal to 30. The third constraint, x2 plus 6 times x3 is less than or equal to 42. So x2 plus 6 times x4 minus 6 times x5 is less than or equal to 42. And now the last constraint becomes x1, x2, x4, x5 are greater than or equal to 0. So now this is the LP model that we'll solve, and once the values of x4 and x5 are obtained using the simplex method, then we can easily find the value of x3. So if both these conditions are met, which in our case are met, then we can proceed with the next step, which is standardization of the problem.